For this example, we will integrate e to the x times sine. Now, to apply integration by parts, we have to make our choice in terms of what's going to be u, what's going to be dv. In this case, we can easily anti-differentiate both e to the x and sine x, and both of them remain about the same when you differentiate them. So it turns out in this case it doesn't really matter what choice we pick. I'm going to go ahead and pick u to be equal to e to the x and dv to be the sine x. But if you chose yours in the opposite way, things would still work out accordingly. This will make du e to the x dx, and it will make v the antiderivative of sine, which is minus cosine. So when we apply integration by parts, we get uv, so minus e to the x cosine of x, and then we subtract away the antiderivative of v to u. So an extra minus sign is going to come out from the minus cosine. So minus a minus is a plus the integral of e to the x cosine x dx. Now typically when we apply integration by parts, the idea is we start off with some difficult integral, and then that resulting integral we get is supposed to be simpler, maybe easier for us to evaluate. In this case, I don't think the difficulty has changed. It's equal in difficulty. So instead of maybe giving up or trying something else, let's just push on one more step and see if we can use integration by parts a second time. Now that we're applying integration by parts a second time, it really does become important in terms of what choice we make for u and the dv. We want to stay consistent. If I switch around and say let u be cosine and dv be e to the x, we would get a correct statement, but we'll just end up undoing our previous integration by parts and get back to exactly where we started. So let's stick with our guns here. U equals e to the x, so dv is going to be cosine x dx. So this makes v sine and du e to the x. Now notice when I've done this second integration by parts, I'm still using u and v, but how my work is organized, I can clearly see at which step I'm using which choice of u and dv. And if you would prefer, you could of course start with u1 and v1 and then go on to u2 and v2 for your second integration by parts. So in this case, the minus e to the x cosine x comes down, and we're applying integration by parts to this integral. We have e to the x cosine. So we have e to the x sine x, and we subtract away from this the antiderivative of v to u. So the antiderivative of e to the x sine x dx. So now after applying integration by parts 2 times, the resulting integral we have is, well, exactly the same as the one that we started. So the integral of e to the x sine dx is equal to this algebraic expression minus that same integral. So what we can do here is just kind of algebraically simplify. So I'm going to go ahead and just summarize with what we have. So that we have this integral we started with, e to the x sine x. It is equal to this algebraic expression we have here. So both terms contains an e to the x. You have a sine x term and minus a cosine x term. And then from all of this, we are subtracting away the integral of e to the x sine x. So what we're trying to do is determine what is the value of the integral of e to the x sine x. So let's algebraically isolate the integral and then solve for it. So I'm going to take the minus the integral e to the x sine x, which is on the right-hand side, and I'm going to add it over to the left. And when I do so, I'll have 2 of those integrals on the left. And that first algebraic expression on the right is just going to remain. And the last thing I want to do here is isolate that integral. So divide both sides by 2. So the integral of e to the x sine x is equal to 1/2 e to the x times sine minus cosine. And since this is an indefinite integral, we need to add on a plus c. So this is a maybe new technique that we've seen here. Once we've applied the integration by parts twice, we ended up subtracting away that original integral. So that allowed us to algebraically isolate and determine the value of the integral accordingly.